This video, I'll cover how to handle a change in internal energy or a change in enthalpy for temperature changes. And the caveat with this is temperature change at constant pressure and constant phase with no chemical reaction. So for all the processes that I'm describing, these are only for the specific change occurring, not for two changes at once occurring. And unlike pressure, we're going to have some non-zero changes in internal energy or enthalpy. So the quantity of specific internal energy is going to depend very strongly on temperature for all substances and all states of matter. So if temperature is changing, it is very uncommon that you're going to have zero for your delta H or delta U. So in order to look at this more analytically, we need to borrow a term that you'll learn much more about in your future thermodynamics class. You may have already learned about this term in your chemistry class. It is the heat capacity at constant volume, and the variable name given to this is C sub V. And CV is defined as, sometimes it's also written like this because heat capacity is a strong function of temperature. Heat capacity is given the thermodynamic definition of the partial derivative of internal energy with respect to temperature at constant volume. This is a bit of thermodynamics notation. Once again, you're going to cover this in much more detail. This parentheses with a V outside just means that V is held constant. And that goes with the name constant, the heat capacity at constant volume. So this is the partial derivative, again, partial derivative of internal energy with respect to temperature. And CV is just one of the properties, as I mentioned, that you'll learn about in your thermodynamics class. There's all other kinds of partial derivatives that you will learn about in the coming courses. The way I like to think of CV of T is if you were to make a plot of internal energy versus temperature, specific internal energy that is, versus temperature, the curve would maybe look something like this. So as temperature is increasing, internal energy is also increasing. I like to think of CV of T as the slope of a tangent line at a given T. So let's say we wanted to know what the heat capacity was there. If we did know the heat capacity, we would know the slope of this curve. So CV of T is the slope. This line is also supposed to be touching the curve, by the way. It's hard to do that on the tablet. Is the slope of the tangent line of a graph of U as a function of T. So in order to find the change in internal energy, notice that we have somewhat of a differential equation here. So we have CV of T is equal to the partial derivative of internal energy with respect to temperature. This is a separable differential equation, and suppose I knew what CV was, and CV is not going to be a constant for most materials, but we can take the dt over to the other side and integrate to obtain this expression. We could say that the change in internal energy is equal to, this should be a partial, by the way, CV dt, again, should be a partial derivative with respect to t. So if I have these terms on both sides, now I have everything isolated. CV is a function of t, and therefore when I integrate it, I have to be mindful of that. So this is going from u hat 1 to u hat 2, and going from t1 to t2. And if I perform this integral, the derivative of any function with no function is the variable itself. So the left-hand side is going to be u hat from u hat 1 to u hat 2. And the right-hand side depends on what the form of CV is. So it's the integral of CV dt for the change in temperature. All right, so the left-hand side you can further decompose into saying it's u hat 2 minus u hat 1, and that is, by definition, delta u. Delta u is equal to the integral of CV dt. And my calculus is a little bit fuzzy. Somewhere along the line, we can say that the partial derivative turns into a total derivative from t1 to t2. And as you've learned in your chemistry classes, if you can further assume that CV is constant, as I mentioned, it's not, but in order to simplify calculations, when they teach you this stuff in your chemistry classes, they want to simplify it for you. If CV is a constant, you end up with the familiar formula that delta U is equal to mCV delta T, where the M would be on both sides. All right, so you probably heard the formula. I think it's Q is equal to mCV delta T. If the energy balance reduces to Q is equal to delta U, then you could say this as well. Q is equal to M delta U hat equals mCV delta T. Now, this was for a closed system. You could also do the same thing for an open system by analogy. So by analogy, you could also define the constant pressure heat capacity. And the heat capacity at constant pressure is defined to be the partial derivative of, this time, enthalpy, specific enthalpy with respect to temperature at constant pressure. And by following an analogous step of the derivation, you can derive that delta H hat is equal to the integral of Cp dt, where once again, if you assume that Cp is a constant, you can pull it out of the integral and have Cp delta T at that point. So I mentioned a couple times now that CV and CP are generally not assumed to be constants. So where can you go to find data for CV and CP? So CV and CP may be found in the only table that we have not used yet extensively. Table B2 is where you can go to find these. Also, Perry's Engineering Handbook. I've mentioned that a couple times in this class. That may be another resource that you can go to find these. Just another couple of quick notes. So in table B2, I'll be more specific and say that only CP is in table B2. However, the heat capacity formulas are related to each other. So for liquids and solids, you can say that CP is approximately equal to CV. And for ideal gases, you can derive this yourself, by the way. You can say that CP is equal to CV plus R. You'll learn about this derivation in thermodynamics for sure. But the point is that if you're looking for CV and you go to table B2, you can use CP interchangeably if it is a liquid. And if it is an ideal gas, you can just subtract the gas constant from CP in order to obtain CV. I'll talk about table B2 in the third video from today. And just to close this video out, I wanted to quickly mention that the textbook has a couple of really good examples. So examples 8.3-2 and 3 are very good, and I recommend doing those for practice. Just write those down. Examples 8.2-2 and 8.2-3. Highly recommend reading these and working through those problems independently. So that'll finish this video. See you in the next video.